So let's look at graphing distance and time. Now, if we had a distance-time graph, we always graph the distance on the y-axis and the time on the x-axis. So if we look at this graph, we see that over here on the y-axis is the distance and time is always on the x-axis. The slope then of this distance-time graph is equal to the average speed. And we looked at calculating slope earlier. If we take 2 points on the graph, like these 2 points, and we calculate the slope, the rise, and the run, we can find the average speed. Now, the units of slope would be the same as the units on the graph. And these units would be meters per second. In this case, this graph, it's centimeters per second, but it's the same units as speed. The slope units are the same as speed. Because really, when we calculate the slope, we're really just calculating the change in distance over the change in time. And so anytime we have a distance-time graph, we can find the slope, and from the slope we can find the speed. If we have an object traveling at a constant speed, like this graph right here, this graph represents an object moving at a constant speed of 2 meters per second. That means every second it's going to travel 2 meters. So after 1 second it's at 2, after 2 seconds it's at 4, and the pattern continues. This motion then, if we were to connect all the dots, results in a straight line graph. We get that straight line that connects those points together. Now the slope of this line will be the speed of the object. So if we want to calculate that speed, all we would have to do is find the slope. Find 2 points and find the rise over the run. Now it doesn't matter what 2 points we use, we can just use these 2 points and we see the rise and the run, how far up it goes, how far over to the right it goes. And if we look on the graph, the rise here, it goes from 2 to 10, so a rise of 8, and from 1 to 5, a run of 4. 8 over 4 gives us 2, and again, the units are the same as the units on the graph, meters per second. We always use the meters per second, the units that are on the graph. Now, when we do calculate the slope, the steeper the line is, the larger the slope, which means it'll be the faster speed. So if we start analyzing a graph, the steeper the slope, the faster the object is moving. Well, let's look at analyzing motions of graphs. And graphs could take a simple form, they also might be complex. Well, here's a pretty simple graph, distance and time, and we have this completely flat line. An object that is not changing its distance as time keeps ticking away. And we want to ask ourselves, what kind of motion is this? So we think physically here, if an object is not changing its distance, that means the object is not moving. It is really at rest. And if an object is at rest, then its distance is not changing, but its time is. This object is not moving at all. Well, what if we had a graph that looks something like this? Now we can see that as the time ticks away, this object starts out, let's imagine a little line there, we work our way up here, it gets a little bit steeper, and steeper, this slope is getting steeper and steeper over time. What we have is an object with increasing speed. It is actually getting faster as time ticks away. The slope at any individual point is increasing. So if we were to compare the slope of a line right here compared to down here at the starting point, notice how much steeper this line is. And if we look at a straight line right here, same idea. Steeper slope, increasing speed. What about a graph like this? And we can probably figure this one out because let's look at the slope. It's pretty steep right here. It gets a little less steep here, and as we work our way through time, we get almost flat. Obviously, this object is decreasing in speed because the slope is decreasing. So analyzing graphs, just looking at the motion, can actually tell us a lot about how an object is moving and where it is at a particular point in time. Let's use these distance time graphs then to actually start studying the motion. And when we have a graph, we can find more details about the motion just by analyzing the graph. And we're going to look at this graph of a car moving. Notice the distance and time. Distance is on the y, time is on the x. And from this graph, we can find a lot out about this motion. This graph shows the motion of a car over a 2.5 hour period. 2.5 hours. And over that 2.5 hour time frame, we can study the slope, notice changes to describe the motion of this vehicle. We can really find the instantaneous speed at any point in time. We can find how long the car stopped or the average speed. There's a lot of information we can get from this picture. So let's use this picture and find some information. The first thing we want to do is determine the speed between 0 and 45 minutes. So we're going to look at our graph, 0 and 45 minutes. We want to find the speed, so we really want to find the slope. 45 minutes, though, isn't on the graph, and we have to do a little bit of calculation. 45 minutes is the same as 3/4 or 0.75 of an hour. And once we know our time, we can do our triangle there, find our rise and our run, and just interpret it from the graph. We go up 75 kilometers in a time of 0.75 hours. Notice we have the units in there, and then we just do the calculation. The slope of this line is 100 kilometers an hour. Well, what if we wanted to find out when the car stopped? Well, remember, the motion of a stopped vehicle or stopped object is when it is a flat line. Well, the flat line is going to occur right there, between those times. Well, just read down on the graph. How long did this car stop for? Well, it stopped at the 1 hour mark, started going again at the 1.75 hour mark, 0.75 of an hour, or 45 minutes, just interpreting that graph. We could also use this information to find the average speed of the car. And remember, average speed is the total distance divided by the total time. Just find the total distance, and there's the point where the total distance occurs. At that point, we know how far the car has traveled, we know the time that it has traveled, we just read the data from the graph, going across to the y-axis to find distance, down to the x-axis to find time, and we see that in 125 kilometers, in 2.5 hours, we can find the average speed of this vehicle, 50 kilometers an hour. And we're going to look at some more distance time graphs in class and study these in a little more detail.